Guess who's back? It's us. Hello, Anthony.
Yes, Ben.
It is time for yet another episode, I think. Do you agree? And also, if not, I mean, since we've already prepared everything, even if you disagree, let's still do it.
Yeah, here we are. Yeah.
I mean,
reluctance.
it is what it is at this point.
Cool.
Not
Let's
sure
kick it
that
off.
counts
Ben.
as Stockholm syndrome yet, but
I was gonna go there, but here we are. All right, Ben. I think we've teased this topic a couple of times around the vector indexing. Kind of talk about what it is today and when to use it, when not to use it, and let's kind of get into where we are. What's the current state of the vector index as part of the CTP, right? As
yeah,
part of the public preview. I think there's some important things to understand where we are from a development standpoint for the vector index. And to be clear, obviously, a vector index adds kind of the storage efficient access into a large data set, similar to a non-clustered index, right? I want to store the data in a particular way so that I can get access to the things that I want faster. So that's the outcome that a vector index brings to the party.
yes.
And as part of the current public preview, there are some things we want to talk about before we get started. So, like vector indexes can't be partitioned. There's no partition support. The table that the vector index is built upon has to have a single column integer primary key clustered index, right? When I add a clustered index, when I add a vector index, the table at which that index is built upon becomes read-only, which
This
means
is
I have
column
to
store index all over again.
totally column store index all over again. Because read-only, which means I can't modify the underlying data. So I have to remove the index, update the stuff, re-add the index, which then becomes kind of a interesting time burden, I guess you could say, on the system. Vector indexes currently can't be replicated to subscribers, but the story here is this: like Ben alluded, when Microsoft came to market with column store years ago, we had very similar, let's say maybe limitations is the right term at the start, but we saw them chip away at that over and over and make that very enterprise class, very powerful feature over time. I encourage you to check the documentation for the current state. I have a link here to that doc and really just kick the tires on where we are, obviously, as part of CTP as we march towards GA for the product. Davide Mallory, who's the product manager for kind of the AI space, has a blog post that kind of this whole demo is built upon. Is about how to build both on a relational side and a physical side, the table structures and the disk layouts and things like that for embedding. So go ahead and check out that blog post here, linked on line 13. And let's get started, Ben. Ready?
Let's go. Maybe let me add one more point. So
Yeah.
far from the features that I've been playing with in SQL 2025, this has been the one that has seen the most change since when we started in 2.0 to 2.1. It's all minor changes from the surface area, like a couple of other requirements have changed and all that. So as Anthony pointed out, please, especially if you're going to either earlier because you're still on 2.0 and don't want to have too many instances, or if you're already on a later version at some point when you're watching this video. As of the time of the recording, there is no later version, but who knows when people are going to watch this 17 years from now.
I really hope no one is watching this 17 years from now.
No, but for example, the creation of the vector index, I've seen tremendous speed improvements from 2.0 to 2.1 by basically running the same code. So but what I'm basically saying is watch this space, but also it's not perfect yet. And I think that is fair because it is a CTP. It's not a final product.
Yeah, exactly. Very very rapidly developing space, from 2.0 to 2.1 on my infrastructure. When I built a vector index, it is now 2.5 times faster between 2.0 and 2.1, right? So that's the level of improvement that we're seeing out of Microsoft and investment in this feature. So we are going to see, all of these walls are going to fall down over time, right?
All right. Let's
Ready?
go.
All right. So I've already created this table in my Stack Overflow embeddings database. Just to kind of recap, I have the Stack Overflow database. I'm going to add this post embeddings table, and I'm going to generate embeddings for all the post titles in the posts table inside of the Stack Overflow database. And I've gone ahead and already created this and populated that with embeddings, but just kind of walk through the table architecture. There we can see our post ID, which is the reference back to the post table. It is primary key clustered as required by the current implementation of a vector index. There we see our embeddings on line 20, 768 dimensions, and created at and updated at, which are the fields to describe when the embedding was created or potentially updated in our system. And we'll cover updates of embeddings in another episode. I'm going to create this post embeddings table on a particular file group on a particular drive in my infrastructure because as I do things like build indexes, I want to be able to observe very easily all the IO patterns, all the storage performance associated with that, so I can help build better platforms for the system. So really, it's not a requirement that it's on an external file group or a dedicated file group or a dedicated disk. It allows me to more easily observe that performance associated with this, right? Cool. Let's go ahead and set my database context. I didn't run this code here. And we'll go ahead and I've already created this table, populate it with embeddings. So we have that there. So the first thing that we're going to do is perform a KNN or an ENN search, so exact nearest neighbor search on our set. And to say something like exact nearest neighbor, Ben, kind of implies something. I have to look at all of the data
Correct.
in the table to
And that's,
do a
by the way, what
search.
we've been doing so far in all our previous demos.
Right, right. And so in our code here, we're going to do a couple things. We're going to generate an embedding or for our search. We're going to do a similarity search across the entire set so we can review all of that. I'm going to give that back to our data or to our query in an ordered way by lower distance to establish the highest similarity. I'm going to turn on statistics.io and statistics time because I want to review the performance implications of what we're doing here when we come back later and add an index. Our query text, the natural language search, is I'm going to find me posts about issues with SQL Server performance. But if you look, I've intentionally misspelled issues to kind of establish like, hey, this is a similarity search, right? I can do things like type in a misspelling and still get a relatively good outcome, right, Ben?
Absolutely.
Awesome.
And I
So
mean, this is what we see every single day. Everybody that's using ChatGPT, that's using Copilot,
mhm.
every day we see how good they actually are, and the lazier we get. Just like when you did your first Google search, you were trying to be like really, really good at being, and now it's just like, okay, it has like 10 typos, but Google will figure it out. And
Yeah,
kind of the same thing here.
what you meant to say was. So let's go ahead and take this code. We'll go ahead and look at the rest of it. So select top 10. I'm going to get the ID, the title. I'm going to get the actual embedding itself. And I'm going to use the cosine distance using the vector distance function for cosine similarity between the query embedding and all of the embeddings in the table and establish that by a similarity score. Other ways that I can search this table are with Euclidean and dot metrics. We'll talk about those towards the end of this video. But what we're going to do here is grab our query embedding, scan the entire table, compare that, and establish the cosine similarity or how physically close those things are, and return the top 10 closest or most similar things from our data set. So let's go ahead and run all this code together and order it by similarity score ascending or the lowest value first, which would be the physically closest in a Cartesian plane current, right? Excellent. So this time we're actually not going to focus on the output. We're going to focus on the performance. And so I have a previous run up here at the top that I copy and pasted in for reference. We'll have that in the code samples. But at the bottom here, you can see in the post table, I read 483,000 logical reads. So it's a pretty good chunk of data in memory. I previously ran this query such that it was in memory. So I didn't do any physical reads. In our post embeddings table, I read 376,000 rows of data. So that's a lot of data to read because I had to scan the whole set, right?
Yep.
But I did get the answer, and it's the most accurate, similar answer from the data set. So let's go ahead and continue this story. To create a vector index, you'll need some trace flags as part of private preview. 466, 471, 13,981. So pretty vast collection of trace flags. Those will need to be on for this session. And if you reboot the server and you need them as part of going to add this to a system, you'll need to have them turned on when the system turns on as global trace flags. This index creation took about 17 minutes to run on the 700,000 rows that I have in this database. I have a smaller subset for demonstration purposes, rather than make you listen to Ben and I banter for the next 17 minutes of that index
People are here
build.
for that, Anthony.
Haha,
Don't
I know.
underestimate that.
I ran this code earlier to build that index for us. And here's the code that I ran. So we have a syntax create vector index. I very accurately named it vec underscore index on the post embeddings table on the embedding field. Width, and the metric is going to be cosine because I'm going to establish the similarity or the angle, the smallest angle between the query embedding and all of the embeddings in the system. Again, Euclidean and dot are options here. I have DiskANN as a type, or disk approximate nearest neighbor is the index structure that is being built, or the graph itself. Currently, that's the only option. And I also establish there's a DOP here, the parallelism of the index creation. If I do nothing, I'm going to use the DOP of the server instance. Or here I have a bunch of cores in the system. I jacked it up to 16 and it actually made it go faster. So your mileage may vary on the performance implications there. So this index is created on our system, and there is a new
I think one
view.
very important thing to point out for people that are trying that on their own data is that the time it takes to create that index exponentially goes up with your data growing. So I did
Yes.
something very similar to what you did. I did 10,000 rows, 100,000 rows, a million rows, 10 million rows.
Mhm.
10,000 rows, easy peasy, took like 4 seconds or something.
Right.
A million rows took me about 16 minutes on my machine. The 10 million rows, well, it has been running for a couple of hours. It hasn't finished yet. The other day, I tried to do it on 25 million rows. It never completed. So
Yeah, and I think it's important to understand the 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 very much so different thing that's occurring when you compare this to a B tree index,
yes,
right? A B tree index is a deterministic structure that's built based on the order of the stuff defined in the table, names, phone numbers, whatever. We're building a completely different data structure called a graph based, which is essentially a tree based off of the similarist things in the database. And so you can kind of see how the complexity of that is very much so different, non-deterministic from the previous B tree based structure. And so you'll find, as Ben described, this is just how the math works, right? So we have this new view called vector indexes in our system. And just to show you that this index is already created, we'll run this code here. And you can see that I have an object ID, an index ID. The type is DiskANN, and the distance metric in use is this thing called cosine, which we've discussed. All right, so built that structure, took 17 minutes. We saw that it took a boatload of IOs to read from our system, but we also want to talk about what we're getting here, right? We're going from an exact nearest neighbor or a k nearest neighbor search, where we search all the rows, to what's called an approximate nearest neighbor search, where we're going to go and we're going to search in a very efficient way into our storage and retrieve a set of rows and return that back to our application in an approximated way. Ben, you want to kind of talk about kind of the difference between the two?
I mean, not an expert, not a doctor, but let me try from a very novice point of view. I think the name is kind of giving it away. One is exact and the other one is approximate. So,
Mhm.
and to be quite honest, I've seen lots of cases where the result was still the same. So it does not
Right.
mean that just because you're approximating something, you're getting worse results. Plus, I mean,
Mhm.
what are we doing here? We're building a vector that may, or an embedding that may even be based on a typo. So, how perfect are we even talking? So, I think the point is with the approximate, the ANN, you're getting much, much faster results. So when you're actually querying like millions of rows, or
Right.
think of even bigger table, that is the way to go. Because at the same time, how much does it even matter? Because it's not like you said, we're not searching a B tree index. We're not searching order number 7247, but we're
Right.
looking for some kinds of posts that are around VB6 or that are around about performance improvements in SQL Server. Uh,
I can only think of one person that's looking for posts in VB6, Ben.
it's a me. Yeah.
It's a me.
So
Okay.
I think that is the big difference here. So your vector distance, the ENN that
Mhm.
we've been using so far in our previous episodes also as well, it takes way more time because it actually needs to read through every single row and compare
Right.
that. Whereas the ANN, it's going through that graph index, it's getting back a set, and that's going to be your result.
Yes. So let's go ahead and run that code. And we're going to show a very much a different entry point into the application or into the data. So we have the same query text, the embedding. We're going to generate the embedding for that. And then obviously we're going to project off or select the ID, the title, the embedding, the distance. But rather than use the vector distance function, which you saw in the previous one, we're going to use the vector search table value function to go and search the structure. What structure we're going to search? We're going to search the post embeddings table. We're going to look at the embedding column. We're going to compare the query embedding to this what's in the table that's similar to parameter here. The type is going to be cosine, and we're going to turn the top 10. Which is important to understand is when I run this code, it's going to do this search first,
Yep.
get these 10 rows or top n rows, and then that's going to get returned as part of the table value function and then joined to the posts table. So just understand the selectivity of what we're doing here. So let's go ahead and run all this code and analyze the performance impact of the vector index on our system. And so let's go ahead and we have our result here. We can see the similarity score, but we're going to focus on the perf part of the house today. I'm going to bring the old numbers into view from the ANN, or excuse me, from the KNN or ENN search that we did earlier and compare. All right. So into the post embeddings table, we did a read. Now this is the embeddings. We're going to go and get a subset of embeddings, and we did 5,960 reads
Yep.
and return those up compared to the previous run, which was 376,333 reads. Dramatic difference in performance there. We're then going to join those to the posts table where the previous run had to read all of them. So 483,961 reads. But now we're only going to hit a subset of posts in the post table, 40 reads. So, 1,000 or 10,000 X improvement there. We then see our read into this thing called vector index graph edge table 6581 and so on. And we have read into
That's
that.
quite a catchy name.
Right. 93 logical read. So you can see that the performance implications of this are dramatic, right? Let's look at the run time. We went from 1.2 seconds before to zero point 0.8. So a little bit almost twice as fast. Obviously, at this scale, it's not quite as visible yet, but imagine it's by 10x or 100x has been described as these things get bigger.
Yeah.
The value or the impact of this, right?
Yeah. So even ignoring the I/O part, which is kind of driving the entire performance of that, obviously. So in one of the tests I was doing, when I was getting like post 2, 3, 4 million rows, you could really see that doing the ENN, the exact search, it would
Yeah.
easily take 15, 20 seconds for a query, which is still looking at what it's doing. It's not slow, but it's not what you want to have in your application. Whereas doing it with the index, it's instant. Boom.
Yeah. And you also look at the CPU implications of this. This will show up as a lot of CPU burn on the system here at 6,516 milliseconds down to 16. So, the vector operation is CPU accelerated on AVX instructions, but that's still going to make your CPU sing. And that, one of the things that we have to do as DBAs is make sure that we're allocating our resources in an efficient way in our systems. Cool. Let's kind of talk about the next part. Go back down towards the end of the demo here. Just a couple ideas I wanted to bring up around the other similarity search metrics that we have. So we talked about cosine.
Yep.
There's also Euclidean and dot, right? And so let's talk about what to use when and what they really mean. So cosine is establishing kind of the measuring the angle between the query and all of the embeddings. The smallest angle is the most similar thing, but that ignores kind of the magnitude or how long the vector is. A vector, can go kind of off in time. It's an arrow that describes the importance of a thing potentially in the data. Cosine is going to use kind of with this thing called a norm, which is going to reduce that to a value between 0 and 1, as we've seen in some of the embedding data that we've worked with. Which one do I use when? So, just looking at cosine, things like text similarity, semantic search, kind of the use cases that we're talking about today. Euclidean is often used since it does bring magnitude to the party or the length of the vector. I can establish a cluster of things in a space. So it's important for spatial data, numeric data sets. And then dot product also includes the magnitude and alignment. So it allows us to rank the most important things in a recommendation system. So I could do things like bubble up the importance of VB6 posts in our environment very easily using things like the dot product. So, any thoughts or comments on these, Ben?
Uh, ish. So
Ish.
I've played a bit with them, and while I understand that that's the theory behind it, and I'm pretty sure there's lots of cases where that really makes a difference.
Yeah.
My recommendation for the viewers and the users out there would be keep it simple for now. I have not
Yeah.
seen dramatic differences when using Euclidean and dot versus cosine, especially when we're talking about text-based data as we have
Mhm.
basically exclusively so far. So the other two would have given me very similar results.
Yes.
I'm not saying that there's no differences. If you look at the pure number coming out of that, you can immediately see some get negative, some don't, and they have like different ranges where they work between and all that. Be all that as it may, we also talked about, hey, you may want to consider using different models and all that. As you're getting started with that, keep it simple. So stick to
Yes.
cosine, stick to one single model and all that, and leave the tuning part for stage 2 or 3 would be my advice here.
Totally agree with that, Ben. All right. You want to wrap it up?
I would say so. What did we
All right.
see today? What did we learn today, Anthony?
Well, I think the biggest thing is to know that, the vector index structure is very much so different than a B tree structure, right? So I like looking at some of the behaviors, we can see that, things like size and dimensionality are going to matter in kind of the structure build time. But the outcome is very similar, right? I want to be able to have, an index, which is effectively is a copy of the data stored in an efficient way for the access pattern that I want to retrieve the data such that I can get to the thing that I want faster, right? You're not going to get a perfect seek like you'd expect in a B tree, but you're going to return a subset of the rows and it's still going to have a very dramatic impact on the performance of your system in terms of disk IO and CPU utilization.
And I think if you look at the structure of a vector, I mean, so far we've mostly looked at 768 dimensions, as we've also
Right.
pointed out. You could have way more than that. Um, I think there's also the answer why a traditional seek on that couldn't really work.
Right.
Because, I mean, it would, you can't just concatenate them in order by that or anything like that, because all of these different dimensions are independent. So, and again, as also pointed out earlier, I think that one important thing is also to say, yes, the vector index, you only get an approximation. The
Mhm.
approximation is pretty good. So,
Very good. I mean, like all things AI, you're gonna kinda get the right answer, right?
famous
Let's
last
play
words.
let's play the
Famous
music
last
then.
words.